Okay, so today I wanted to talk about Tapoya. I have to warn you that my talk is ill prepared today, so I may be very, it may be very incomprehensive, but I'm sorry, we'll have to live with that. Okay, so let me start from a definition. As topology on an S category is Grothendieck topology on the homotopy category. So if it's S category T, then it's an S topology on homotopy category of T. So as site then is a pair T tau consisting of S category and Grothendieck topology, S Grothendieck topology. So let me make a remark. The conceptual explanation of why we define topology on homotopy category of sequential category is that as categories represent infinity one categories, and stability axiom of Grothendieck topology implies that all higher, that is greater than one morphisms should be covering because they're invertible. So that means that basically our definition of Grothendieck topology only depends on one morphisms that is on homotopy category.
Grisha, sorry, could you remind stability axiom?
Yes, certainly. One moment, one morphisms.
Okay.
Yeah, sure. Stability. So, one moment. So I have written down somewhere here. Okay, so the stability axiom basically says that I'm writing it down for the basis of Grothendieck topology, is that it basically just says that if we have an isomorphism, then it belongs to the Grothendieck topology. In higher category world, an isomorphism is an invertible morphism of any rank, so it's an isomorphism, hence F belongs to KFC. So yeah, I think it's like this. I can check real quick with McLean Moerdijk. Okay, wait a moment. I can try to check it really quick. So sorry. Okay, so for growth-inject topology, not for basis. Okay, so let me write it down. For growth-inject topology, stability axiom states that if S belongs to J of C, then H upper star of S belongs to J of D for any arrow H from D to C. Okay, so let's try to derive the fact that if we have an equivalence, then I guess this equivalence belongs to so this equivalence is covering. So well, we know that the maximal sieve is J of D if H is an equivalence, then particular that means that it means that we have G such that codomain of G is equal to D, and we consider HG in S. So particular we have if we have TC, then we can consider H minus 1 Uh, so, hmm. Yeah, no, I guess we will just have to assume that the stability axiom is what I stated before. So any isomorphism is an K of C or K basis of Grothendieck topology. Maybe we can derive this from the stability axiom for sieves, but I don't know how to do it right now. So I'm afraid we will just have to roll with that. Okay. So this was somewhat garbled conceptual explanation of why we should define Grothendieck topology on homotopy category. Okay. So
Grisha, sorry, could you repeat it again, please? What you write it before the stability axiom?
okay, so I stated some axiom for the basis of Grothendieck topology. It says that any isomorphism belongs to any isomorphism forms an element K of C. So if we have one element family which consists of an isomorphism, then it belongs to K of C, where K of C is the basis of Grothendieck topology.
Yeah, okay, but before it.
Before it, so the stability axiom for sieves states that that SB is sieve.
No, Grisha, even before.
Okay.
Yeah, this part.
Okay, so I stated that all invertible morphisms should be should be covering for Grothendieck topology, which is just one of the axioms. And then I stated that since we have a model for infinity one category, then all higher morphisms, that is morphisms of rank higher than one, should be invertible. Therefore, if we have some notion of Grothendieck topology on a higher category, that necessarily implies that all higher morphisms belong to set topology. Therefore, we are only interested in distinguishing those one morphisms which are in Grothendieck, which are covering for the Grothendieck topology. And that's why we define Grothendieck topology on homotopy category.
Sorry, Grish, so you mean Grothendieck topology on higher category, you mean if you view it as a one category. So you just cut all higher morphism and there you have a Grothendieck topology.
Well, not exactly. So first of all, I don't discard them. I just say that we identify those morphisms, those one morphisms which are related by higher morphisms.
Okay, I see. So you define, you have Grothendieck topology on homotopy category, yes?
Yes, but so I tried to explain conceptually why we do it only for homotopy category and we do not define Grothendieck topology on the higher category itself. And the reasoning was that if we have some notion of Grothendieck topology, then necessarily all invertible morphisms should be in Grothendieck topology, meaning that they're all covering morphisms. But in this case, all higher morphisms necessarily should belong to Grothendieck topology, right?
Mm-hmm.
And that's why we just need to look at the homotopy category and not look on the higher category itself.
Mm-hmm. But isn't Grothendieck topology something that we could define for a one category? So what do you mean for a higher category?
Well, I don't mean anything specific. I'm just saying some abstract nonsense that if we had some notion of Grothendieck topology for higher category, then we necessarily should count all higher morphisms as part of this topology.
Okay,
it is not a rigorous statement, it's just some hand wavy thing.
Okay. So, and then after all this, here you have conclusion that we have to define then Grothendieck topology only for homotopy category.
Yes, yes.
Okay, now it's clear.
Okay. Besides, we already know how to do it for homotopy category because it's one category.
Mm-hmm.
So it's quite useful. Okay. So let T be an S category in the universal view. Then we define three steps on this category as countervariant functors to simplicial sets from this category taken from the opposite category. So for any pre-stack F, we can consider a pre-sheaf of sets which is defined like this. Okay, so obviously this is a simplicial set, so it makes sense. The universal property of homotopy category now implies that we can take this functor P0F to sets, and we can take the localized category, the homotopy category, and we get a factorization like this. And so after remarking that this construction is functorial in F, we get a functor like this, which is defining for us a functor from homotopy category of pre-steps to the category of pre-sheaves on homotopy category, the simplicial category. Okay. So definition. T tau be small s state. For any in pre-stacks, we have an associated sheaf of connected components. E0 tau of f. It is a sheaf on the site, on the usual site, homotopy category T in cross-stack topology tau. Okay, so that was the first part of the definition. The second part states that a morphism F to G called tau covering if the zero tau of f is surjective as a morphism of sheaves on homotopy category of T. If it's homotopization is tau covered. Okay. Clearly, for any two x and y objects of our category tau, the morphism from x to y such that C generated by it from category T is covering induces covering morphism of representable three steps hx to hy. Okay, so proposition morphism from F to G in the category of pre-stacks is tau covering if it satisfies the local surjectivity condition. For each x an object of T and any morphism hx to G in homotopy category free steps. So we should have the following lifting diagram if we had a morphism from hx, then we should have a morphism from hu to hx such that the following diagram homotopically commutes. In other words, f is covering if only if for any x in G, so G, locally, homotopically lifts to an object over F. So basically, in very crude terms, what we should imagine is that we have G, which is covered by some representables. So we have this covering morphism, which can be thought of as an inclusion. Then we have a morphism from F. And we say that, well, everything here is up to homotopy, of course, but basically the idea is that this morphism should lift to give us a covering of F. To give us, well, not covering, but at least an object over F. Meaning we can think of it as an open subset. But once again, this is just very crude analogy of what is happening. Okay, so let me give a corollary of this statement. So composite morphism coverings is itself covering. Second, if we have a Cartesian diagram, and F is covering, this is the notation for covering morphism, for the family of covering morphisms. This implies that F prime is covering for G prime. 3. If we have the following composition morphisms in pre-stacks, then if the composite belongs to coverings, then P belongs to cover. Finally, a partial converse of the second statement is that, sorry. So if we have a Cartesian, homotopically Cartesian diagram like this, and we know that we have covering morphisms F prime and P. This implies that covering morphism, that F is a covering morphism. Okay. So that's the description of covering morphisms in pre-stacks using this functor of components. Now, I'd like to move on to some simplicial techniques which are useful to define stacks. So consider the category of simplicial pre-stacks. This is the standard notation for, well, it's not standard, it's standard for our seminar. For this category of simplicial objects. So F star then is functor from simplicial category from the simplex category to our category of pre-stacks. Category of simplicial pre-stacks is naturally tensored, cotensored over simplicial sets. How this works? Well, we have tensoring of the following form. It's a contrariant functor which stands Fn to the following union or coproduct. And exponential is defined, so the cotensoring is defined by an adjunction. Okay, so the category of simplicial pre-stacks as basically any category of simplicial objects in the model category carries a ready model structure. The ready model structure, because there's only one. Here is the ready model structure with equivalences defined level wise, and vibrations defined by the following formula. We have a morphism like this, which is induced by respective inclusions. And this morphism should be a vibration. Vibration in the category of pre-stacks. Then for vibrations are defined via the lifting property, or we can give a straightforward definition, but I don't want to do this. Okay, so here, notation-wise, remember that we had these little underlined strikes, but here f lower star to the power of a is just this thing. Okay, so if there is a simplicial set A, then f mapped to fa is a right functor in Reedy model structure. Okay, so okay, so we have a derived functor of this, the right, so it's the right equivalent functor. Therefore, we have the right derived functor of this. Okay, so let consider an inclusion IN of truncated simplex category. So this is a category of P's with full subcategory of ordinals which are less or equal to M. Then we have a natural restriction morphism from all simplicial pre-stacks to truncated simplicial pre-stacks. It has a right adjoint. There are right left adjoints, which are denoted like this. IN, which is a right adjoint, and IN allowed, which is the left adjoint. So we have the following adjunction identities. And if we take this in reversed order, then we get the following definition. So the skeleton is by definition the following thing. And the co-skeleton is by definition another thing. So that's the first. The second part is that F lower star is called unbounded if F lower star to the string is an isomorphism. Okay, so quick remark. Conjunction yields the following fact. So we have an isomorphism, well, at j is less or equal to n of the following functors. Okay, so an adjunction between i's induces the following isomorphism of form spaces. Okay, in particular, we have the following isomorphism. And even more particularly, we have an isomorphism like this. This follows from the fact that delta n is isomorphic to skeleton n of delta n plus. Okay, so the following lemma. Functor co-skeleton n from simplicial pre-stacks to simplicial pre-stacks is a right equivalent functor. Meridian. read the model structure. Simply show pre-stacks. Corollary of this lemma is almost immediate. We can consider the right derived functor of length for skeleton, which is a functor, of course, on homotopy categories. Now we have, well, not of course, but actually we have relative versions of this skeleton and conskeleton functor. I will give a formula to compute the relative version of the skeleton functor. So we have homotopical pullback of the following form. So obviously, F is a simply show pre-stack over G. Okay. In particular, we can interpret the functor, the right derived functor of relative coskeleton as a derived nerve of the following form. In what sense it is a derived nerve? Well, if we have a morphism like this, in category of simply show pre-stacks, then we can consider a morphism like this from F0 to G. So this is a constant diagram where in each dimension we have just G. Then we can consider such a morphism in just in homotopy category of pre-stacks. Then we can consider a representative, which is a fibration. And then we can consider the nerve of this fibration. The nerve is a simply show object augmented over G, which looks like this. NOF is augmented over G, and hence NOF belongs to former category like this. And so we have an isomorphism of zeros, of derived functor of zero stall skeleton, and this derived nerve. Okay. So now we can use this simply show nonsense to define the notion of hypercovering, and we do it in the following fashion. So, sorry, wait a moment. Okay. So definition. So consider an S site, then morphism simply show pre-stacks F G del hypercover or just hypercover if for any n the induced morphism R delta m, which is just Fn, to R d delta m, homotopically taking homotopic Cartesian product over G R delta n star with R delta. So this should be this morphism is a covering homotopic category like this. So we define the notion of a covering in this homotopic category by saying that at the level of p zeros, we should have a cover. So we have an associated sheaf, and if this morphism of sheaves is epimorphic, is an epimorphism, then we say that it is a tau cover. So applying this to our simplicial situation, we say that a morphism of simplicial pre-stacks is a hypercover if this morphism of just pre-stacks is a regular cover. So that was a definition of morphism in simplicial pre-stacks. Now we take the homotopic category of this category. If one of the representatives is a hypercover. So another way to state this definition is by saying the following. So F from F star to G star is a T hypercover. If and only if for any n greater than 0, Fn to this n minus 1 coskeleton, relative coskeleton, is a covering in homotopic category of pre-stacks. Okay. So now we want to obtain steps from pre-steps. And for this, we will need the notion of local equivalence. Okay, so then we can consider comma category of the homotopy category. And we have a natural projection here from comma category of simplicial category, from homotopy category of comma category of simplicial category. And here we have tau-induced topology. So the setup is that we have some site, as usual, and a site, and we have an induced Grothendieck topology, and we have this projection, and we just pull back along this projection. And we have an induced Grothendieck topology on the comma simplicial category of T. Induced Grothendieck topology. Okay. So now let me define an associated sheaves for higher homotopy groups for any pre-step. So let F be pre-step, and X is an object of T. Then for n greater than 0, the sheaf PNFS is defined via the following formula. Okay, so what is so what is GX? GX is a morphism from the comma category to the category itself, which forgets X. And we get a morphism in homotopy category of pre-stacks, which just takes well, basically, we can even say that it's not only in homotopy category, but in the usual category. So we have a morphism from pre-stacks, a restriction morphism from pre-stacks to pre-stacks over comma category. Okay, so this thing is a sheaf. The sheaf on homotopy category with induced topology, and it's called end homotopy sheaf. Pointed at S. So what is S? Well, S is just S is just a morphism from a point to should like this. So yeah. Okay, so now let's move to the definition of P-star equivalence. Morphism between three stacks. So P lower star equivalence. Local equivalence. If first of all we have an isomorphism on zeros homotopy sheaves, so it's an isomorphism in homotopy category of T. And second, for any object in T and any section of this form and any integer greater than 0, the induced morphism of homotopy sheaves is an isomorphism on homotopy category on sheaves in sheaves on homotopy category of comma category. Finally, I highlight these points. Finally, we say that a morphism in homotopy category of three stacks is a P-star equivalence if one of the representatives is okay. So remark any equivalence T or sorry, steps on T is the P-star equivalence. Because well, basically because it induces an isomorphism of homotopy sheaves in trivial Grothendieck topology, and hence in any Grothendieck topology. Okay. So now let me skip a little bit. So with the notion of P-star equivalence, we now may proceed to defining the local model structure. So theorem. Closed model structure. On pre-stacks, which is called local projective model structure, such that equivalences are P star equivalences. Coffee. So this is the notation for this category with this model structure. So cofibrations don't change. And well, this model structure is cofibrantly generated. Proper. That is, I think, irrelevant. So yeah, we have such a model structure. And from the description of this model structure, one may guess that, in fact, it is a Bose-field localization of the model structure or projective model structure on pre-stacks, and fibrant objects are precisely what we will call stacks. So let me state this result. Moment. Okay. So corollary to this theorem. With respect to the class of hypercovers of X. So those are hypercovers over X. So we localize in such morphisms, and what we get is precisely the category of pre-stacks and vibrant objects are stacks. So yeah. So we can state it in the following form. Definition. A hypercover H star to the representable pre-stack semi-representable if for any n greater than 0, Hn is isomorphic homotopic category to a coproduct of representables. So that's first. And second, an object with stacks has hyperdescent for any x in the objects of T. Presentable cover. The induced morphism if x isomorphic. Well, we have an isomorphism in homotopic categories. Of the following things. So it's an isomorphism in well, basically we have an equivalence of simplicial sets. Okay, so now I will state the definition, which I think will conclude my talk today. Well, maybe I will wave my hands some more, but basically tau is an aside. Stack on T tau is a stack which satisfies hyperdescent condition in the sense which was declared above. The model category, this form is called model category of stacks. So homotopic category of this homotopic category of stacks. Yeah, and topology tau set to be subcanonical. So we have a very similar definition to the usual cross-index topology, where subcanonicity meant that for any object of a category, the representable pre-sheaf or pre-stack in this case is a stack. So this morphism factors through homotopy category of stacks. And finally, this thing here, which belongs to homotopy category of simplicial sets, or R tau, is the derived from space computed in pre-stacks or stacks. Okay. So I think, I think that's it. Let me just very briefly explain what we did. So we started, I will explain without any details, but we started from infinity one category, which can be modeled by basically by anything. It can be modeled by S category, model category. Actually, it may be an exercise to produce the same thing that we produced here for model categories, but it's really not that hard. You just replace everywhere simplicial categories with model categories and it works. Maybe, I don't know, Siegel space or something. Then we consider the category of pre-stacks, which is basically just a category of simplicial sets of contravariant functors from this infinity one category to simplicial sets. Then what we do is we define hypercovers, which are simplicial objects constructed from covers gross-index topology tau on homotopy category of T, and we localize these equivalences in these maps. So hypercovers are, as we've seen above, basically just simplicial objects which are augmented over just pre-stacks. And so basically what we're doing is we consider nerves of certain regular covers in homotopy category, and what we obtain is a hypercover, and we just require that morphisms from realizations of this simplicial objects to our representable functors should be equivalences. Well, yeah. So another way to see this is by considering local equivalences, which are defined using homotopy sheaves. So basically what we did here is we constructed higher category of sheaves on a higher category. So basically all we did in this term, we just learned some tools which are needed to obtain such a construction. I think that's it for my today's talk. Are there any questions? Maybe suggestions, comments?
Oh, it's nice, thank you.
Okay. Thank you for attending. And I'll see you then next time, whenever that will be. Okay.